In this video, we're going to explore the log normal distribution as an alternative distribution for simulating random lambdas for our wolf PVA. If you click on sheet 2, you should see the following setup. Before we begin, we're going to simply review what lambda is, and if you remember, it's just the ratio of two numbers. Two population sizes to be specific. It's nt plus 1 divided by nt. So for example, if we enter nt as 20 and nt plus 1 as 22, we would calculate lambda as cell D3 divided by cell D2. That generates a lambda value of 1.1, and that represents a 10% increase in population size from its base population size. We can get that by entering equals lambda minus 1. That gets us back to the actual growth rate, and you can see that we've formatted cell D5 as a percentage to reflect that. If NT were only 18 individuals, then lambda drops down to 0.9, and that represents a 10% decrease compared to our base population. So lambda is simply the ratio of two numbers. Now, in our wolf PVA, we use the normal distribution to draw random lambdas from a distribution whose mean was 1.3 and whose standard deviation was 0.4. And if you remember, we used the norm.dist function to simulate that distribution. Let's find that now. Norm.dist. This function has four arguments. The first argument is x, which we have referenced in cell J13. The mean is given in cell G2, and we'll anchor that. And the standard deviation is given in cell G3. We'll anchor that as well. We'll enter false for the fourth argument because we don't want the cumulative distribution. And if we pull this through, you'll see that we've created a graphic already. So what this means is, with this distribution, with a mean of 1.3, standard deviation of 0.4, what is the probability that we would reach in and grab a random lambda that had the value of -1? And you can see that Excel is returning a 0. What is the probability we would draw a 1? Excel returns a 0.75. So it's much more likely that we would draw random numbers someplace in this range, but very occasionally we might draw a random number as high as 3 or as low as just above 0. To draw a number from this distribution, we can enter a percentile or a probability in cell G4. So for example, if I enter 0.4 in cell G4, then we can use the norm.inv function to return the associated lambda value. So let's find norm.inv. And this time our probability is referenced in cell G4. The mean of the distribution is still in cell G2, and the standard deviation is in cell G3. So what this means is if I specify a percentile or a probability, then I'm returning the associated value on this bottom axis here. So what this means is, let's find 1.2, and what that means is 40% of the numbers are to the left and 60% of the values that could be returned are to the right. And that can be driven home by entering a few different cases here. Let's put down 0.3 instead. Now our lambda value is 1.09. So 30% of the weight under this curve falls to the left of 1.09, and 70% falls to the right. If we drop this even lower, 0.1, now we have a lambda value of 0.79 along this x-axis. So 10% of the lambdas that could be drawn fall to the left, and the rest of the values, 90% of the lambda values, fall to the right. And we use this exact same function to draw a random lambda. And here we just used norm inverse, but we used a random number for our first argument, and then kept the mean in cell G2 and the standard deviation in cell G3. And if you press F9 then, each of these numbers represents a random lambda drawn from this distribution. We indicated that this distribution was just fine for our wolf population because there was no opportunity of drawing a 0 or lower, and that can't be the case. If lambda is 0, the population is extinct, and it cannot be a negative number. So what do you do if, for example, the standard deviation is higher for your population of interest? Well, here the normal distribution doesn't work quite as well, does it? You see that there is some opportunity to draw a random lambda that's negative. So what alternatives do we have? Well, the alternative we're going to explore in this video is the log normal distribution. And there's two reasons why we want to consider the log normal distribution. The first reason is this distribution will never return a negative number. But the second reason is that your lambda values are very likely log normally distributed instead of normally distributed to begin with. And the rest of this exercise we're going to have a demonstration that will drive this point home. We've set up a simulation of 500 trials down column A, and we've assigned the number 1 to each and every trial down column B. And our simulation is going to be very simple. And this simulation is inspired from a paper called Log Normal Distributions Across the Sciences, Keys and Clues, which was published in Bioscience in 2001. And the reference is at the bottom of your screen. The simulation will go as follows. We're going to simulate NT as a random number between 1 and 6, and NT plus 1 as a random number between 1 and 6. Then in column E, we'll add the two numbers. In column F, we'll subtract them. In column G, we'll multiply them. In column H, we'll divide them. And then the next step after we generate these numbers is to visually look at these results across all 500 trials and see how these numbers are distributed when we look at them in aggregate. So first, for NT, let's use the rand between function, and we'll enter the number 1 for the bottom number and 6 for the top number. And that will draw a whole number between 1 and 6, and we can use this value for both NT and NT plus 1. And we'll copy that through for all 500 trials. Now in column E, let's add those two numbers together. So that would be C13 plus D13. In column F, we'll subtract them. That would be C13 minus D13. In column G, we'll multiply the numbers. That would be C13 times D13. And in column H, we'll divide them. And in the spirit of lambda, we're going to divide D13 by C13. So NT plus 1 divided by NT. Let's copy these all the way through. And now let's create those frequency histograms that I mentioned previously. To make a very quick frequency distribution in Excel, we can use a tool called the pivot table. And the first thing we're going to do is select our data, and we'll actually select over to cell I-12 and then all the way down. We'll be looking at this column I in just a minute. Then let's head up to the Insert tab and choose the Pivot Table button. The Pivot Table dialog box comes up, and you have two things to specify. The first is you need to indicate your data in a table or a range. We've already done that. And then second, you need to choose where you want the pivot table report to be placed, and we'll place it in a new worksheet. So a new sheet will appear, and you should see the following setup. So your pivot table is actually contained on the left side of the screen, and on the right side of the screen are your tools for building your pivot table. If you look at the right box, in the upper right box, you'll see that the headings here represent our column headings for our data set. And what we need to do is to specify which of these columns will be the rows or the columns, and which is the values we want to summarize. And for this exercise, we're going to first look at the two added numbers, nt plus nt plus 1. So we'll choose the Add button, and we'll simply grab it with our mouse and drag it into the row labels section. And you'll see that Excel has started to build the pivot table. It's listed all of the possible results down column A. So 2 results when both nt and nt plus 1 are both 1, and 12 results when both of those numbers are 6. Now for the sum values, we're going to grab the count variable and put it into the sum values section. And so what you can see is that Excel has recorded the total number of times that I returned a 2 for my answer, 12 for my answer, and every answer in between. So all 500 trials are represented here. You'll see that my spreadsheet returned the number 2 11 times, the number 12 17 times, and the number 7 85 times. And that should make some sense, right? Because 2 can only happen in one way. Both of the numbers must have been the number 1. And a 12 can happen in only one way. Both of the numbers must have been a 6. But a result of 7 can happen in many ways. For example, nt could have been 5, and nt plus 1 could have been 2, or nt could have been 6, and nt plus 1 could have been 1. There's lots of different ways to generate that result. When we make this pivot table, you ought to see that Excel has created a new tab called Pivot Table Tools. And it has two tabs, Options and Design. Under the Options tab, there are two buttons that are important. One is the Refresh button, which if you press, it refreshes the spreadsheet. It generates new random numbers from that ran between function, and hence a new set of results. And the second is this pivot chart, which works just like every other chart in Excel. We're going to choose the column chart and display it. Once you have the chart selected, you'll see that there's a new tab called Pivot Chart Tools, and you'll have lots of options for handling your chart, including adding the axis titles, which I'll do now. So again, if we click anywhere on the pivot information itself, go to the Options tab, we can press Refresh and get 500 new sets of trials, and each time very quickly displaying our results as a frequency histogram. Now, how would you characterize these results? Would you say these are normally distributed? I would. Let's see if this is a general pattern. Well, they look pretty normally distributed to me. Let's see what happens if we subtract the two numbers. So we'll pull out the added value and we'll pull down the subtracted value. And again, let's refresh a few times and see if a pattern emerges. And these also look fairly normally distributed. What happens if you multiply the two numbers? Here now, I think you'd agree that we'd be hard-pressed to say this has a normal distribution. Let's try the last one, division. And again, really tough to say that this is a normal distribution. So what can we do about that? Well, let's click back on sheet 2, and one of the things that we're going to do is to take the natural log of these two divided numbers, and that's just ln h13, and we'll copy this through. And before we copy it through, though, I'd like to round these, so I'm going to couch this value in a round function, and the second argument is the number of digits, and we're going to round them to just 2 decimal places. And now these values should be in our pivot table as well. Let's go back to our pivot table. This time we have to press refresh because we've added new data to our pivot table. And now let's take a look at the log of the divided numbers. Now these don't quite look normally distributed, but one of the things that you might notice is the way that they are grouped, because they're not nicely grouped into these units like we had from our previous examples. So let's group these numbers by right-clicking somewhere down column A, and we'll choose Group. And let's group them by 0.5. And now when you select those and press refresh, you should be able to see a more normal distribution, and that's what the log normal distribution means. It's two numbers. When you multiply them or divide them, if you take the log of those numbers, then the log of those numbers has a normal distribution. That's what the log normal distribution is. Make sense? Okay, let's go back to sheet 2 now. Let's take a look at what this log normal distribution would look like. And just to begin, we'll enter the number 1.3 and 0.7 in cells H2 and H3. And we'll create the distribution down column L. And you might guess that we'll use a function that's similar to the normal distribution, norm.dist, that pertains to the log normal distribution. And you'd be right, it's called log norm.dist. Let's find it. It has the exact same syntax as our norm.dist function. We enter x as cell J13. The mean will be in cell H2. Let's anchor that. The standard deviation will be in cell H3. We'll anchor that. And the cumulative will be false. And if we pull this through, now you can see in red the log normal distribution when the mean is 1.3 and the standard deviation is 0.7. So you can see that they don't correspond 1 to 1. Why might that be? Right. These numbers represent a number that is not a logarithm, not a natural log. These numbers, this distribution, assumes that the numbers themselves have a log. So let's go ahead and enter the natural log of cell G2 as our mean. And now you can see that the two graphs are starting to converge and look more and more alike. Not a perfect match. The log normal will never go negative, And you'll see that it has this broader tail as well. And you can play with the standard deviation and use different values to simulate your population. Now, just like we did with the normal distribution, we can enter a percentile and then use an inverse function to generate the random lambda or x. So let's find that function. It's called lognorm.inv. Again, this has the exact same structure as the norm.inv. We enter the percentile, the mean, and the standard deviation, but this time the assumption is that the numbers have a logarithm. The reading of these results is exactly the same. So if I drew a random number that was 0.1, then the corresponding lambda value would be 0.53. That means that we find 0.53 on the bottom axis here, and that means that 10% of the curve is to the left of that number and 90% of the curve is to the right. And we can use that same exact function but replace our percentile with a random number, and that would be a mechanism for drawing random lambdas from the log normal distribution. So if we press F9, we're generating random lambdas. So there you have it. You may see that people use the log normal distribution to simulate random lambdas for a population. And once again, there are two reasons for this. The first is that the log normal distribution will not return a negative lambda value. And the second is that lambda is probably distributed as the log of the divided nt plus 1. It's the natural distribution for modeling random lambdas. Okay, we'll see you next time.